Hello, my Science Alliance, my IGCSE offshoot. How are you? We're doing moments, which is one of my favourite lessons. I'm not going to tell you what moments are just yet. Basically a moment is how much something turns. There, I did just tell you. I'm excited because I get to talk about Jurassic Park. First thing I'm going to do in this lesson about how much things turn is show you a scene from my absolute all-time favourite film. The best film ever made, in fact, Jurassic Park. Now, it is the best film ever made, but the director, Steven Spielberg, it wasn't about the details. And actually, it was his lack of caring about details, which makes it such a fabulous film. But we were going to look at one particular scene where there are at least 3 details that kind of, if you think too much about it, it's just nonsense, right? I'm going to show you a scene that has a problem with the dinosaur. So look for the dinosaur-related sort of issue, inaccuracy. There's a physics-related inaccuracy, which is what we're really going to be talking about today. And there's also a storytelling, not inaccuracy, but a problem, a bit of an issue, okay? So if you don't know Jurassic Park, I don't really want to give you any spoilers, but dinosaurs come back to life and get put in a theme park and then they escape. Who would have thought? This is towards the end of the film. The power has all gone off. It's come back on, but the systems are all offline. So Lex, who is a computer expert, is in this little room trying to put the systems back online. And she's an expert. She just needs a couple of minutes. That's all she needs. But as you'll see, there are some issues. So here we go. I can't show you the actual clip because for copyright reasons, but I can show you some photos. So here we go, right? This is Dr. Alan Grant. This is Dr. Ellie Sattler. They're both sort of experts in like dinosaurs and prehistoric plants. They're pushing against this door because here is Lex. Lex needs a bit of time on the computer to get the system back online. But as you can see, I don't know if you can just make out this kind of shadowy shape behind the door. This is a triangular shaped window. You can see the eye here of a velociraptor, which is trying to get in. So Dr. Grant and Dr. Sattler are trying to keep the door shut to keep the dinosaur out so that Lex can get the system back online. It's all very tense. And the computer is in the foreground here. And that is a velociraptor. Okay, so there's Dr. Grant. You see now, there Dr. Grant is sort of in the background pushing the door. And in the foreground, you've got Timmy, who's Lex's brother, and Lex in the foreground, just to set the scene. All their problems would be solved if only they could reach the gun. But the gun is on the ground just too far away in front of the door. Dr. Sattler tries to reach the gun, but she just can't reach it. And she turns to Alan and says, I can't get it unless I move. And obviously she can't move because if she moves, then there won't be enough force pushing against the door and the dinosaur will get in and it will all be game over. So we just have to forget about the gun. The dinosaur gets its look, velociraptor claws just getting through the door. There's Dr. Alan Grant trying to push the door shut. Oh, there's the velociraptor breathing against the window. Here, cut back to Lex looking at the computer screen with Tim looking over her shoulder. So what's wrong with this scene in Jurassic Park? Obviously, there's nothing wrong with it because Jurassic Park is the most perfect piece of filmmaking ever. But can you see a storytelling reason, a paleontology dinosaur reason, and a physics reason for why this scene isn't very realistic? Answer at the end. Right. The activity that we're going to start with to just like really draw you in to why physics is relevant to all our lives. Have you got a tablespoon with you? If you have, can you, while I get rid of this annoying like shadow light line, can you please think of how many different ways can you spin this tablespoon? If we're going to be physicsy about it, I should, instead of spin, say rotate. How many different ways can you rotate this tablespoon? I'm, at the moment, holding it flat horizontally and sort of rolling it towards me. Let's say that direction doesn't count as 2. So like rolling it towards me and rolling it away from me. That would be one way of rotating the spoon. Should we say that planes don't count as well? You really should know what I mean by plane. We're doing IGCSE Physics. So like there's a horizontal plane, a vertical plane. Like the x-axis is one plane, the y-axis is another plane, the z-axis would be another plane. So rotating the spoon like this horizontally or turning it vertically and rotating it. We'll say that that's all just one way of rotating a tablespoon. How many different ways can you think of? On Facebook yesterday, someone got 7. Just going to have a jiggy with these lines. Wow, that is making no difference. There we go. It's not great telly, is it? me just rotating a tablespoon out of view. I feel like this isn't a theatre of science highlight when it comes to engaging activities, but I can't show you because that would be cheating. Okay, I've got 1. I've got 2. I've got 3. Why can I only do 3? How would they do 7? Anyway, should we move on? Hopefully you've got a few. What I wanted to do was introduce what a pivot was. We need to know what a pivot was before we do anything else. A pivot, it's easier to show than it is to explain. On these incredibly dull diagrams of seesaws that physicists are always drawing to learn about moments. A pivot is basically when something turns, the pivot is what it turns around. So on a seesaw, this triangular bit, this top bit here would be the pivot because the seesaw is turning around the pivot. Yeah? It doesn't have to be at the end. So like on a diving board, for example, the pivot would be there because the diving board is sort of turning. Yeah, it's turning. It doesn't have to turn all the way. It's turning around this pivot. A good way of working out what the pivot is if you imagine sticking a pin into the thing. If the pin goes through the pivot, the thing can still turn. So if I pinned my pivot of my seesaw there with that pen, the seesaw would still be able to turn, right? If you stuck a pin through that bit of the diving board, it would still be able to turn. If someone like nailed that bit of the diving board to the wall, the diving board can no longer be a diving board. It can't move up and down. If you nailed that bit to the wall, that bit would still be able to move. All right. So on your spoon, if you have rotated your tablespoon, can you think of all the different ways that you rotated it? Can you think of where the pivot points were? We just took it all the way up a notch. Where are the pivot points on your tablespoon? Because the pivot would have... This is a good way of showing, isn't it? Like a child might think, oh, okay. I mean, you probably are a child, but like a young child. I don't know. Someone who hadn't understood me, child or adult, might think, oh, all right, so the pivot on a seesaw is always there. But this is quite a good way of showing you that the pivot can move on an object. So if you spun your tablespoon round like it was kind of the propeller or whatever of an aeroplane, then the pivot point would be in the middle. You could put a pin through that bit and you could still spin it around that bit. So then the centre would be the pivot point. If you put your finger on your spoon, like say on the spoony bit of the spoon, whatever it's called, and span it round like that on the table, then the pivot point is now on the spoony bit, isn't it? It's where your finger is. So you can literally, your finger can be the pivot point. Or if you turned it upside down, and you could have put your finger on the very end of the handle, and then that would have been the pivot point. You see what I'm saying? All right, I think we've done enough to lead you into the first, we're easing in gently, the first sheet that I have for you, which is, where's the pivot? And I've got you a bit more stuff to think about in case you finish. But yeah, what I want you to do is just check that you've understood what a pivot is, and then also start thinking about like how things turn around. So we've got 6 items here. I want you to just write down, or if you've got this free printout from my website, you could be circling it. Here you've got a door. So the hinge of the door is labelled A, the door handle is labelled B, and the door frame is labelled C. Which one of those is the pivot point? You've got a balance like you see on sort of the Libra star sign with the 2 sort of, what are they, 2 dishes on either side. So A is one of the dishes, B is the very base of the scales, and C is the top bit that bounces on the top of the scales. This thing, my kid loves them, calls it stick up down, like the barrier that lifts up and down when you go into a car park. You've got the base, which is C, A, which is the point where the base meets the stick, and you've got the very end of the stick, which is B. A pair of scissors, which are chopping a ribbon. The ribbon is A. The centre of the scissors, where the sort of little screw is, that's C. And the handle is B, where there's a pivot on a pair of scissors. A pair of chopsticks. You've got a prawn being grasped at the end. That's A. Where the chopsticks cross over, that's C. And the very end of the chopsticks is B. And on a spanner, you've got the very end of the spanner that your hand is on for A. The middle of the spanner for B. And the what is it? Bolt. The bolt that the spanner is grasping is C. Which of those are the pivot points? I've given you an example here, but I've told you already, haven't I, that the seesaw, the pivot is in the middle. And if you finish that, which you quite possibly have by now, can you say which words might complete this sentence? A seesaw is still when the turning forces are something and something. You might want to draw a diagram to help you think about that. A seesaw is still when the turning forces are something and something. Is the answer, or are the answers, small, large, adjacent, equal, opposite, pushing, pulling, squirrel, something else? And the equation for how strong a turning force equals something times something. Can you think about what might go in those gaps? But we'll do a bit more about that in a sec. And if you're really bored, you know what I'm going to say, don't you? You can always like and subscribe, can't you? Could do that. If you're just joining me, you could just like and subscribe, I'm just saying. I'm trying to give you a bit of silence and thinking time. For number one, I mean, you might have a good idea. You might straight away sort of have an instinct for what words I'm looking for. But can you draw a diagram and try and actually understand it? Rather than just thinking, oh, it's probably this. These words usually go together. Could you actually explain number one, I suppose? If you think you've got the answer, could you explain it to someone who doesn't know the answer? Shall we go through it? Yes, I just can't wait to teach you it. Okay, number one, where's the pivot on a door? Well, the door is opening and closing, so the door is turning. So the pivot is A of the door. You could stick a pin through the hinge and it wouldn't make any difference to whether the door was turning or not. So A is the pivot point, it's turning around the pivot. C is the answer to number two. It's this bit in the middle, so the scales, the bar of the scales is kind of moving up or down, but you could stick a pin through the very centre of where that bar attaches to the base and it wouldn't make a difference. That stick up down, I sort of told you, hadn't I, already? Yes, it's where the stick joins the barrier bit. Pair of scissors is that bit in the middle, isn't it? So the handle and the blades are both turning around that pivot point in the middle. I mean, someone has literally stuck a pin through it, and that's how scissors work. The chopsticks, it wasn't a great little picture, sorry. It's where the chopsticks are crossed over. That's where the pivot point is. And the spanner, I was quite pleased with that one because I thought, oh, you might be getting the idea that the pivot point is always at the end. You might have said B, but actually the whole spanner is turning around the bolt, isn't it? So it's C is the pivot point of the spanner. Is that okay? Because the bolt is staying still, so it's almost like there's a pin through it. And this description, well, yes, a seesaw is still when the turning forces are equal and opposite. What does that actually mean? We'll get to the equation in a sec. A seesaw is still when the turning forces on it are equal and opposite. Well, you probably get the equal part. Like if you put two boxes on either side of a seesaw and they both push down exactly the same amount, you probably know from experience that the seesaw would be balanced. Yes, it would stay still. The idea of them being opposite forces is, I think, a little bit weird, isn't it? Because, everything we've learned so far has said that The force acting when a box is sort of sitting on a thing is the force of gravity. So one of the forces. So gravity is pulling that box down, and gravity is also pulling that box down. So surely gravity is acting in the same direction. So why are those forces opposite? Well, when it comes to moments, moments are how much something is turning. So when it comes to moments, we're looking at the clockwise moment and the anti-clockwise moment. So this box on this side is pushing down, which is kind of trying to make the seesaw turn in the anti-clockwise direction. Anti-clockwise. And this box on the right-hand side is trying to push the seesaw so that it turns in the clockwise direction. So in that way, we wouldn't say the forces were opposite, we would say the moments were equal and opposite. The anti-clockwise moment is equal to the clockwise moment. And this is the principle of moments, which is so important I wrote it down. The principle of moments: if something is balanced, the total clockwise moment, that everything trying to push the seesaw turning on the clockwise direction, is equal to the total anti-clockwise moment. Right. I've got an activity for you that it turned out on Facebook to be quite dangerous, actually. What I want you to do is 3 different things, really. A moment is basically how much something turns. So I want you to go over to the nearest door, maybe the door to your room that you're in, or maybe like a cupboard door. Don't put your fingers really near the hinge, right? Don't put your fingers anywhere near the hinge so that your fingers will get trapped and hurt, okay? Don't do that. But without putting your fingers really near the hinge of the door, can you have a little experiment and see if you can work out what 2 things can you change that affect how much the door turns? I'll give you the questions here. So the equation for moment, how much something turns, is something times something from the pivot. So what I want you to do is have a little investigate of the door without putting your fingers near the hinges or without trapping your hands in the door. Be careful. 2 different things you can change which will affect how much the door opens. And then if you've done that, if you're really confident, you could tell me the units for moment, please. What's the units of a moment? And you could also tell me, is moment a force? Is a moment a force? So I'm hoping that now you've got your door and you're very carefully doing different things to your door to see if you can change how much it opens. What 2 things? Have you had a go at the first one? Do you want to come over to my door? Oh, again, with the exciting telly. So, some of you on Facebook were saying things like the mass of the door or the weight of the door. It's not the mass or the weight of the door, but they do affect the thing that it is. One of them most people on Facebook were getting, because they were thinking it was fairly obvious, right? If you've just joined us, we're talking about what 2 things you can change that affect how much a door opens. I'll open my door slightly. What can I do to affect how much it shuts? Well, I could change the force that I push the door with, right? Hopefully most of you were sort of thinking about pushing the door. So if I do a gentle push, if I apply a small force to the door, it does not shut very much. If I apply a large force to the door, then it shuts more. So it's force is the first one. What's the second one? What else can you change? The other one is the distance, how far away the force is from the pivot. So the pivot, in our case, is these hinges on the door. So if you push with exactly the same force, very near the hinge, wow, I really pushed that quite hard, then you will not get much of a turning effect. If you push with the same amount of force, really far away from the pivot, you get much more of a turning effect. And if this door was 3 times longer and you pushed it with the same amount of force, it would shut even more. So it's how much force you push the door with, or the moment, how much something turns, is related to how much force you apply, and also the distance from the pivot. And in fact, there's slightly more than that. I'll tell you what, I'll show you it and then I'll come back to the door. Always useful. Moment equals force times perpendicular distance from the pivot. I'll give you a question about this at the end, which will help you to understand it. But the perpendicular distance from... Oh yeah, no, I haven't. There's no spoilers on the board. The perpendicular distance from the pivot. Are you okay with what perpendicular means? Like, these lines are parallel because they're running next to each other like train tracks. These lines are perpendicular. They are at right angles to each other. So if the force is going in that direction and the pivot's over here, that is the perpendicular distance from the pivot. The distance, a line drawn where the force and the pivot distance are at right angles to each other. So for example, if I apply an absolutely enormous force really far away from the pivot of this door, but I'm pushing in that direction, like towards the door frame, that is not the perpendicular distance from the pivot, because the distance between the force and the pivot is in the same plane as the force is acting. Okay, they're parallel, so it's not making any difference at all. The force has got to be at right angles from the distance to the pivot. Whew, okay. Well done for coming to this lesson on YouTube, because I explained that much better than I did on Facebook yesterday. What are the moments for force then? Come on, we've done this loads. Whatever you do to the numbers, you just do the same thing to the units. So if the moment is equal to the force times the perpendicular distance from the pivot, the units for moment are just the units for force, which is the Newton, times the units for distance, which is the meter. So the unit of a moment is a Newton meter. It's nice, isn't it? Be careful, it's not newtons per meter, right? That would be if you were dividing newtons by meters, and you're not. You're timesing them together, so you just write them together like that. The Newton meter. So the last question, is moment a force? Is a moment a force? You should really be able to answer this like that. Is a moment a force? No, it's not. How do you know that? Because forces are measured in newtons, and moments are not measured in newtons. Moments are measured in Newton meters. So I'm really annoyed, I'm really sorry, I haven't bothered to go through this PowerPoint and take out all my references to turning forces, because when I taught this lesson a couple of years ago, I kept saying that a moment was a turning force, and it's not, is it? It's not a turning force, because if it was turning force, it would be measured in newtons, it's not as measured in Newton meters. So every time you see the words turning force, I want you to tut at me, please. A moment is not a force. Right. Let's have a look at a practical example, and then I will give you some fairly straightforward questions to do, and then we'll dig into how an IGCSE question might try and trick you. Well, not trick you, but really test your understanding. For example, it's a bit of a dog theme, this lesson. Here's Patch. Patch weighs 5 newtons and is 1 metre away from the pivot of this seesaw on the left-hand side. I know it's not, but it doesn't matter. Just take my word for it. Patch weighs 5 newtons and is 1 metre away from the pivot of the seesaw. Fluffy weighs 4 newtons and is 2 metres away from the pivot of the seesaw. Which one of these dogs is going to end up getting dunked in the water below? Well, the anti-clockwise moment, how much the seesaw wants to turn in the anti-clockwise direction, is equal to the force pushing on it times the perpendicular distance from the pivot, which in this case is Patch's weight pushing down times 1 metre, which is 5 Newton meters. And the clockwise moment, how much the seesaw wants to turn in the clockwise direction, is Fluffy's weight pushing down, that's the force, times the perpendicular distance from the pivot, which is 2 metres, which is 8 Newton meters. So this is a turning force on a clockwise, oh my goodness, I said turning force, a clockwise moment of 5 Newton meters. Wait, an anti-clockwise moment of 5 Newton meters and a clockwise moment of 8 Newton meters. So it's going to be Fluffy that gets dunked. Phew. Are you all right with that? I'm just going to give you loads of those questions. Is that okay? It's fairly easy, isn't it? Just to plug the numbers in at this stage. How much the thing is going to turn is equal to the force pushing down on it times the distance that force is away from the pivot. So work out on which side the moment is greater, and that's the side that the seesaw is going to turn. Yeah? Brilliant. Here you go. So you've got 6 different questions here. Dogs fall onto seesaws from above. Don't think too carefully about it. Who gets dunked? Moment equals force times distance. So you've got Patch, who weighs 5 newtons, 3 meters away from the pivot on the left-hand side, and Shep, who weighs 8 newtons, 2 meters away from the pivot on the right-hand side. Which one of those is going to get dunked? The next one, you've got Smoochie, who weighs 3 newtons and is 3 meters away from the pivot on the left-hand side, and Lara on the right-hand side, who weighs 6 newtons and is 3 meters away from the pivot. Which one's going to get dunked? Third question, Tinks weighs 2 newtons and is 2 meters away from the pivot on the left-hand side. Fluffy weighs 4 newtons and is 1 meter away from the pivot on the right-hand side. The fourth one, Woofy weighs 1 newton and is 5 meters away from the pivot on the left-hand side. Can you enjoy? I'm really enjoying saying this. Tinks weighs 2 newtons and is 200 centimeters away from the pivot on the right-hand side. And Terry weighs 5 newtons and is 3 meters away from the pivot on the left-hand side. It just sounds like some sort of cool song. And Doggo is 1 kilogram and 2 meters away from the pivot on the right-hand side. And finally, the last question, number 6. The dogs are balanced, so the seesaw is not moving. It is, if you like, in equilibrium. Gumdrop is 10 newtons in weight and 3 meters away from the pivot on the left-hand side. And Janet, we don't know their weight, but they're 2 meters away from the pivot. Can you please tell me, how much does Janet weigh? If you can't do a couple of these questions, like if you can't do question 5, don't worry, it might be because you haven't been to all the lessons. So that's not you, that's just you not knowing a thing because you weren't at the lesson. So don't worry about it. I will talk you through it. And if you've got finished, I gave you like a little sort of gentle puzzle. You've got a seesaw there with 2 balls that are exactly the same size, and exactly the same distance from the pivot. But the seesaw has turned. It's not balanced. It's not balanced. How has one of the balls caused the seesaw to turn? What's happened there? I'll give you the answer to the first question so you know you're on the right track. If Patch weighs 5 newtons and is 3 meters away from the pivot, then the amount that the seesaw wants to turn in the anti-clockwise direction, the moment in the anti-clockwise direction, is that force, which is Patch's weight, because weight is a force pushing down, times how far Patch is away from the pivot, which is 5 newtons, times 3 metres, which is 15 newton metres. And I've written turning force, and I shouldn't have done, should I? Should be moment, I would write. I'll change that. I'll change that for when I do this lesson again in 2 years' time. Oh, that's nice. There's lots of people just joining us. If you're just joining us, then you've probably got all the information you need, to be honest. Don't need to answer these questions on the board. Depends if you've seen all the previous lessons. This lesson is going to be saved on catch up. It's just going to be on YouTube forever now until YouTube, I don't know, decays away. So if you want to watch from the beginning, you can. Or if you want to stick around, that'd be nice too. All right, yeah, so Shep. Shep, you just do the same thing. So the clockwise moment, the moment in the clockwise direction is 8 newton meters, Shep's weight pushing down, times 2 meters, which is Shep's, how far Shep is from the pivot in the perpendicular. So here you've got a good example, right? You can see the distance from the pivot and the direction of the force are perpendicular. They're at right angles to each other. So that moment is 16 newton meters. So you would say that Shep is going to be the one getting dunked, right? Okay, and we'll do the last question. Actually, I'll maybe do it on the board. Are you ready for me to go through the answers? I'll go through the answers, and then you can be sort of finishing the last question if you like, and then I'll go through the answer. All right, so Smoochie and Lala, I mean, you could probably see straight away, actually, a lot of you, that if the distances are the same and one weighs more, then it's going to move in the clockwise direction. But I wouldn't ever do that. If you're in an exam, always write down your working. So Smoochie, it's the force times the distance, which is 3 times 3, which is 9 newton meters. And Lala, in the clockwise direction, it's 6 newton times 3 meters, which is 18 newton meters. So it was Lala that was getting dunked. Tinks, the anti-clockwise moment is 2 newtons times 2 meters, which is 4 newton meters. Gasp! And in the clockwise direction, it's 4 newton meters times 1 meter, which is the same. So yeah, it's actually balanced, is that one. That's why when I'm on the seesaw with my child, I have to scooch along because I weigh a lot more than they do. So they sit right on the end and I scooch along till I'm further near the pivot. So there's less of it. I'm producing less of a turning force, even though I weigh more. Yeah, good, right? Physics in everyday life. Woofy and Tinks. Did you spot that there's 200 centimetres there that you definitely need to change into 2 metres? So then you can do the sum, and it's 1 times 5, which is 5 newton meters from Woofy. And Tinks is 4 times 2, which is, wait, what? 4 times 2, which is, what have I done there? That didn't make sense, did it? Have I done that wrong? The turning force on the, oh yeah, right, yeah, of course, because 2 times 2 is 4. Yeah, I see. Sorry, I haven't bothered to put the maths in, but yeah. The turning force in the anti-clockwise direction from Woofy is 5 newton meters, and in the clockwise direction, it's 2 newtons times 2 meters, which is 4 newton meters. So yes, I'm correct. It is Woofy that gets dunked. Right, this one with Doggo, let's do a little bit of recap of what weight and mass means, because it's just always good to do revision. You had to remember that mass is not the same as weight. For the purposes of your GCSE, mass means sort of how much stuff is in a thing. It doesn't just mean that, but you can think of mass as being how much stuff is in a thing. Do you remember? So the mass of this pen is the same if it's on Earth or if it's on Mars or if it's just floating around in space. It's always got like the same amount of stuff in it. But weight is how much force is pulling on the thing. So on Earth, this pen weighs a certain amount, but if it's floating through space, it doesn't have any weight at all. It's still got a mass, but there's nothing pulling on it because there's no gravity affecting it in space. So weight is equal to the mass of something times, on Earth, little g, the gravitational field strength, which is 9.8. So Earth has got a gravitational field. We've talked about this. Earth has got a gravitational field, and when mass comes near Earth, it starts to feel the effect of Earth's gravitational field. And how strong Earth's gravitational field is 9.8 newtons per kilogram. So per 1 kilogram. So if 1 kilogram happens to be on Earth, it's getting pulled on with a force of 9.8 newtons, right? Sometimes we say 10 to make the maths easier, but for your IGCSE, you've actually got to remember that it's 9.8. So if it was 2 kilograms, it'd be 9.8 kilograms, 9.8 newtons per 1 kilogram of force. So you'd have to times that by 2 to get the thing's weight. Isn't that all right? So doggo weighs 1 kilogram. So it's just the weight of doggo is 1 kilogram times 9.8 newtons per kilogram, which is just 9.8 newtons. So doggo weighs 9.8 newtons. If we say that it's 10 newtons to make our life a lot easier, then you ended up with a turning force of 10 newtons times 2 meters, which is 20 newton meters in the clockwise direction. And what was Terry? He was 5 times 3, so that was 15 newton meters in the anti-clockwise direction. So it was doggo who was going to get dunked. Is that all right? And finally, let's do this other one. You've got Gumdrop, who weighs 10 newtons, and in fact, I'll just show you. This last one here, I'm just going to write out for you. Apologies if some of you are really comfortable with the maths. This might be a little bit tedious. If you're watching on catch up, you can just skip ahead. But some of you aren't comfortable with the maths, and it's good to talk it through. So this seesaw is balanced. The proper physics way for saying that is it's in equilibrium. So if it's in equilibrium, if it's balanced, then the moment going clockwise must be equal to the moment going anti-clockwise, right? So I'm just going to write that down on the board. I'm going to write down brackets 10 newtons times 3 meters, close brackets, is the same as equals whatever Janet's weight is times 2 meters. Yeah, that's what that means. That times that must be exactly the same as that times that, because the seesaw isn't moving. So I've ended up with, let me see that. I've ended up with 10 newtons times 3 meters equals Janet's weight, whatever it is, times 2 meters. So let's just simplify a bit. Let's say 10 times 3 is 30 newton meters. So 30 newton meters is the same as Janet's weight times 2 meters. So this is good, isn't it? We're timesing on this side. So when you rearrange an equation, if you're timesing on that side, you've got to divide on the other side. So I'm going to say 30 newton meters divided by 2 meters is equal to Janet's weight. Is that all right? Oh, I feel all physics teachery when I start writing numbers on the board. I don't get to do this very often. So we've simplified that down to 30 newton meters divided by 2 meters equals this mystery thing. So the numbers, 30 divided by 2 is 15. And what do we do with the units? Well, look, the meters cancel out. You've got meters on the top and on the bottom, so they cancel out and you're just left with newtons. Is that right? Yeah, it is, because we were looking for a weight. Hooray. So that would be a good indication that I was correct. So Janet weighed 15 newtons. Whew. Okay. Do you know enough about moments to tell me what was wrong with that scene from Jurassic Park? If you got the storytelling issue and the paleontology issue, well done, but I'd rather that you got the physics issue. So, the first problem is this velociraptor is massive. It's taller than an adult, which is not really what velociraptors were like. Here's a beautiful diagram. Thanks, Wikimedia Commons, of someone comparing all the sizes of velociraptors next to a 5'9" human, and you can see they're coming like up to the knee, basically, even the smallest one. Also, you can see they've got feathers, haven't they? So I guess there were 2 problems. By Jurassic Park 2, they had realised that dinosaurs had feathers, and they changed it. They started giving them feathers. But in Jurassic Park 1, we didn't know that. So that's the paleontology problem. The velociraptor is too big, and also it doesn't have any feathers. The storytelling problem is, Tim, mate, what are you playing at? Just go and get the gun. I understand you've been through a lot, you've had an electric shock, but you can still walk. Just go and get the gun. Problem solved. So Tim's the problem when it comes to storytelling. But the problem physics-wise is Ellie Sattler saying, I can't get it unless I move. Ellie, she can move, can't she? She's like 20 centimetres away from the pivot, from the hinge of the door. So I don't think Ellie Sattler moving is really going to make any difference. She could have got the gun herself. She's not producing very much turning force. She's not producing much moment. And come to think of it, actually, Dr. Grant, you should budge up a little bit as well. He should be putting his weight. Yeah, I mean, he probably wants to avoid the claw, I suppose. Fair enough. Right, a little note. You can add moments together. So here's a little example of how you do that, because I've said total clockwise moment equals total anti-clockwise moment, which is where that becomes relevant. So here, if you had two dogs on one side, you literally just add the moments together. So the anti-clockwise moments in this case would be, this is Patch, isn't it? So you do the weight of Patch times Patch's distance from the pivot, which in this case is 5 newtons times 3 meters, which is 15 newton meters. But to find the total anti-clockwise turning force, you've got to take this little person into account as well. Not person, you know what I mean. So you've got to do their little weight of 2 newtons times the 1 meter that they are away from the pivot, which is 2 newton meters of moment, and then you've got to add those together. So you'd say the total anti-clockwise moment on that seesaw is 15 newton meters plus 2 newton meters, which is 17 newton meters. And then the other side's easy. You'd go, okay, 4 newtons times 5 meters. The clockwise moment is 20 newton meters. So in this situation, it would be whatever that dog's name was that got dunked. Yeah? Okay. Are you ready to do one of those questions for me? Yeah? Think you can do it? All right, have a look at this. The seesaw is balanced. What is Shep's mass? So it's just the same as the example that I showed you. You've got 2 dogs now on the left side of the seesaw and only 1 dog on the right side. One of the dogs on the left-hand side weighs 3 newtons and is 1 meter from the pivot. And the other dog is 3 meters from the pivot, but we don't know the mass of that dog. I want you to find it out. And on the right-hand side, you've got a dog weighing 4 newtons, which is 6 meters away from the pivot, and that's that. So have a quick go at that for me, please. The seesaw is balanced, or it's in equilibrium, to put it a better way. If you're struggling to get started, the first thing I would write if this was an IGCSE question is the seesaw is balanced, so the anti-clockwise moment is equal to the clockwise moment. That's the first thing I would write down, just in words, and then I would write that using maths, like using the numbers. All right, so to help out the people that are struggling, the next thing that I would do is, like I say, just sort of write that out using these numbers. So the clockwise moment is, well, I just work it out actually, yeah. The clockwise moment is 6 meters times 4 newtons. So you know that the seesaw, there's a moment of 24 newton meters trying to push the seesaw in the, well, that's wrong, isn't it? A moment trying to push, because that sounds like a moment is a force. There's a clockwise moment acting on the seesaw of 24 newton meters. So you know that all the moments added together on the left-hand side must also equal 24 newton meters. Please double check your answer. If you think you've finished, just give it a double check just to make sure that you have got the right answer. I'll give you 10 seconds and then I'll go through it. All right, let's go through it then. So the total clockwise moment is 24 newton meters, which means that the total anti-clockwise moment is also 24 newton meters, yeah, because the seesaw is in equilibrium. So I would just write that out the same way that I wrote it out before. So I know that moment produced by Shep plus the moment produced by whatever this little dog is called is equal to 24 Newton meters. So 3 newtons times 1 meter, the turning force created by a little dude, plus 3 meters times whatever Shep's weight is, equals 24 Newton meters. And then let's do what we did before, just simplify this. So it's 3 Newton meters plus 3 meters times mystery weight equals 24 Newton meters. We've added 3 Newton meters on that side, so we can take it away on that side, and we end up with 3 meters times mystery weight equals 24 Newton meters. Take away 3 Newton meters, which is 21 Newton meters. All right, so hopefully this is fairly straightforward now. 3 meters times something equals 21 Newton meters. We're timesing by 3 on this side, so we can move it over and divide by 3 on the other side. So we end up with the mystery weight is 21 Newton meters times divided by 3 meters, which is 7. And again, the meters cancel out, and you got 7 newtons. Yay! So the answer is 7 newtons. Yay! But it's not, is it? Ah, because they were looking for the mass. It's just the kind of evil thing they will do in IGCSE. That's why you've got to keep checking the question. So you've got Shep's weight. How do you find Shep's mass? Well, I would expect you to know now that weight equals mass times gravitational field strength on Earth. So it's up to you whether you said that little g was 9.8 or whether it was 10. It won't really make a difference after rounding. So you rearrange this to get, okay, Shep's mass equals their weight divided by little g, which is 7 newtons, good that we've got that, divided by, let's say, 9.8 newtons per kilogram to be correct, which is 0.7. Oh man, when you look up and realise that you've got a battery low warning on your phone, so you might not have heard anything that I said. Really sorry if you didn't. Did you get all that? That we found out Shep's weight, and then we had to use the equation mass equals weight divided by little g to find out that Shep's mass is 0.7 kilograms. Okay, 0.7 kilograms. Right, if you've done that, can you please get a scrap paper, bit of scrap paper that is A4 size ideally, and just fold it so that the long edges are touching each other. Fold it like that, yeah? So the long edges are together. This is my Lego story time about owls last week that I don't need anymore. Fold it in half so the long edges are together, and then can you fold it in half like that again and again? So fold it in half so the long edges are together 3 times, so you end up with a sort of stick of A4 paper, yeah? And then if you've got a little bit more scrap paper left, can you please scrunch up 2 little balls of paper, just small balls. I can flip you around now, can't I? You've got that. Ah, yeah. Yeah, 2 small balls of scrap paper, right? There we go. This thing is going to pretend to be a dog throwing stick. I don't have a dog. So it was a dog theme to this lesson. You've seen people who walk dogs, you might have one yourself at home. They've got like a cup on the end of a long plastic stick, and you put a ball in the plastic cup and you throw it, it makes the ball go further. Why is that? It's because moment's in it. So if you folded a piece of scrap paper in half 3 times, what I want you to do, please, ideally, if it was a proper science experiment, the balls should be the same mass. I don't know if they are, but can you put one very far away? Now, where is the pivot, in fact, to this? Where the pivot is depends, doesn't it? If I was throwing, I'd be flicking my wrist, so the pivot would be my wrist. I'm wondering now if, to get more of a moment, a greater turning effect, I should keep my arm and the paper straight and use my elbow as the pivot, so that when I put my ball up there, it's even further away from the pivot, so it feels even more of a turning effect. Maybe I'll do that instead, but that's quite hard to do. Can you get 2 little balls and put one ball right at the end of your paper and one ball towards your hand, like maybe sort of in the middle, right? So hopefully the paper that is at the far end, because you're applying the same force because you're pushing it the same amount, but this little ball is further away from the pivot, you should find that the top one goes further. I mean, if you're like me and you're in a tiny little room, you won't really be able to tell the difference, but it's fun and it'll help us remember. You ready? I'm not sure you saw that didn't work, but I'm not going to blag it. I'm just going to do it again. Yay! Super fun times. Yeah, so that's how those dog balls work. Same amount of force you apply, but because the distance from the pivot is further, you get a greater turning effect, and therefore you get a greater displacement. It goes further. Right. Very last question, because I'm not totally sure that you've understood this idea of that the force has to be perpendicular from the distance to the pivot. And there was a question very similar to this, didn't involve dogs, but a question at IGCSE or at GCSE that tripped quite a lot of people up while I was teaching. So I thought I'd show you a version of it to just check that you've understood. You've got Janet playing on a Ferris wheel in 3 different ways. You've got a little Janet on a Ferris wheel and she's in the carriage, which is directly above the pink circle. So the pink circle is the pivot, okay? The Ferris wheel is rotating around the very middle. So that's the pivot point. In the first one, Janet is sitting directly above the pivot in the carriage and is 10 meters away from the pivot. In the second image, Janet is in like the second carriage down and is 8 meters above the middle carriage, if you like. And in the third picture, Janet is in the very middle carriage, 10 meters away from the pivot. Which wheel experiences the greatest moment, please, if it's the same dog in each picture? Which wheel experiences the greatest moment? This is my moment. Which one? Hopefully you're saying the answer is definitely not the first one, because Janet is sitting directly over the pivot. So she's 0 distance from the pivot. So there would be no turning effect there at all, would there? If Janet was perfectly balanced over the pivot, there would be 0 turning force, because however much Janet weighed, whatever the force was pushing down, you'd be timesing it by 0 because it's 0 distance from the pivot. So there's no moment there at all. Between the other two, it's a bit trickier. The weight of Janet is pushing down. Sorry, I should put it below, shouldn't I, if it was a force diagram, but I had to put it above. But the weight is pushing downwards in both cases, but it's the distance that is perpendicular to that weight. So in the second picture, the distance that is labelled is not the distance that is perpendicular to the force. That is parallel with the force. So you can see the distance between the pivot and the force is smaller than in the third one, where Janet is as far away as she can possibly be from the pivot. Is that okay? You're just looking at the distance that is perpendicular. Phew. Hopefully that makes sense, but they will quite often try and catch you out with that. Right, that is the end of the lesson. It's a good thing too, because my throat is very sore. I hope you've enjoyed this lesson on moments. We are skidding towards the end of our forces and lesson module. We're doing electricity after this, after Christmas. I'm going to go over to my Facebook page, see if anyone has left me any comments. Thank you very much to the people who leave comments. Thank you also very much to the people who just lurk. I honestly value all of you equally, because it would be no good at all if everyone commented. It would be absolute anarchy. But if none of you commented, it would also make me very sad. So let's see if any of you have commented today. Oh yeah, some comments! Now if there's too many comments, it's often a bad sign. It often means I've been writing backwards when I shouldn't have been. But let's see. Maybe you're just all super engaged and giving me the answers. It might be that. Or it might be, you've frozen, you didn't notice that your battery was running low and you didn't see that alert pop up on your phone, so it froze. Oh, hello, Chloe! Oh, well, that's nice, isn't it? Chloe just says, loving the dog theme. Thanks, Chloe. Oh, Bastian. Oh, I'm liking this. Yeah, Bastian sends me screenshots to say, is this right? That is really good that you do that, because it means other people can see that and learn from it. Bastian says, would where I've put arrows be pivot points as well? Oh, no one's brought this up before. What do you reckon? So, yeah. I mean, that's good. It's not a mistake that I made, because I hadn't labelled them anyway. But yeah, what do you think? Would where Bastian has drawn arrows here be pivot points on this one of the kind of Libra scales? I mean, I suppose the answer is we would need to know whether these scales were free to move. If it's just like metal, metal spokes there that are soldered to that bar, then obviously not. But yeah, I know what you're thinking. That's a little basket on a chain, isn't it? So yeah, you're absolutely right. Yeah, very good. That would be a pivot point, yeah, because it would be swinging in that direction. Or a really evil IGCSE question would sort of point out that that was a pivot probably, and then but you'd have to know that it's not that pivot that is affected. Well, yeah, that's complicated, isn't it? Because that little thing there is directly below the pivot, which is of course what you want, because you don't want that to be swinging to and fro. You want there the weight to be acting parallel to the pivot. Oh, that's so cool. Do you see what I mean? You want all the weight of this, let's say it's rice, to be acting downwards exactly underneath the pivot, because if you pulled this little cup to the side so it's hanging at an angle, then it wouldn't be parallel to the pivot and it would like swing. So yeah, you're quite right, Bastian. Well done. Great question. Okay, let's see what else is put. Oh, hello, Olivia. Oh, oops, you couldn't see A. Oh yeah, is that the one where I just stuck A like right over some bit of the picture that was loads of black? Yeah, sorry. Units, force and time. Oh, force and time. No, time does not come into moments at all. It comes into momentum, doesn't it? Which is really confusing because they sound very similar. The other dog is 3 newtons. I was going to go, yes, because I just have total faith in you. Honest answer is I can't remember, but I'm sure I would have written it on the board. A seesaw is still when the turning force is equal and adjacent. Oh, thank you. I can completely see why you were thinking that. Yeah. Oh, that's smart. The forces... Oh my goodness, that's so clever, isn't it? Have you seen what Olivia's done there? Because I phrased it as turning forces. I said that a seesaw is balanced when the turning forces on it are equal and adjacent. And actually, if you're thinking of the forces being measured in newtons, yeah, the forces on it are adjacent because they're both going, they're parallel, aren't they? Man, that is brilliant thinking, which is why you've got to be really careful how you phrase the question. And I shouldn't call it a turning force because, yeah, we weren't talking about turning forces, were we, in the end? We were talking about the moments. So the moments on it have got to be equal and opposite, anti-clockwise and clockwise. But yeah, you're quite right. Actually, the forces pushing down on it do have to be distant. Man, you lot are absolutely on fire today. I hope that the people who are watching this on catch-up bother to wait for this bit. They won't, will they? They won't bother watching this bit. Oh, man, they've really missed out. Could Timmy get it and hand it to the... Yeah, exactly. Exactly, blooming Timmy. Why don't you just say 10 times 2 equals 30? So 2, yeah, I definitely could have said that, yeah. Coulda, shoulda. Shet will be dunked, Lala will be dunked, neither Woofy will be dunked, I don't know, 15, the ball is heavier. Oh, I didn't do that answer either! Man alive! Yeah! Well done! It's because we haven't let him... Oh man, I haven't explained that. Yeah, it's because the one where the 2 balls were exactly the same, but the seesaw was not balanced. Yes, it's because this ball is heavier. It's denser. It would have to be denser. The particles in it would... I'm writing backwards because I'm excited. And I'm forgetting that I'm not on Facebook. Oh, it's because I am on Facebook, reading comments on Facebook while streaming on YouTube. Confusing. Yeah, we haven't done about density, but you could imagine that this one is a bowling ball and this one's a bowling ball and this one is a balloon, the same size as a bowling ball. It's just that the particles in it are closer together. So it does weigh more, even though it's the same size. Yes, thank you for that, Olivia. Phew, that was lucky that you lot were here. Okay, I'll have a quick refresh, but there aren't usually like masses of comments on the YouTube version of this lesson. Indeed, a lot of you come because there are no comments. Good, I think there's the same amount of comments, which means that I can go and start planning for next week. So thank you everybody who has come to this lesson. Oh, thanks Olivia, it's sticking around to the end. Yeah, thanks. All right, you lot, thank you for those absolutely magnificent questions. Yeah, I will see you next week. Yeah, that's it really. I'll just see you next week. I'll give you some homework at some point before then. If you want to support me, please do go to my About section on YouTube and sign up to support me to fund these lessons, and just like and subscribe because that'd be great as well. Thank you to the people who've liked this, really makes my heart glow rainbows. And yeah, I'll see you soon. Bye.